All right, let's roll this thing. All right, so we're gonna go on a little history trip. People studying astronomy, this eventually leads to universal gravitation, but it takes like thousands of years here. So suppose you go back in time, 1,000 years or more ago, right? You're not a skinny person, like, okay, what's like the structure of the solar system, kind of how everything in space works. Right? Pretty universally, everybody would have told you the wrong answer. What they would have said is, oh, well, it seems like Earth must be at the center of everything, and it looks like everything's going around us. Like I see the moon going around us, which is true, right? But if you look at the motion of the moon in the sky or the motion of the sun, it's really hard to distinguish the difference. In fact, they kind of look identical, right? They just kind of go across the sky. It looks like they're kind of orbiting, right? And all the other stars and planets, kind of same thing too, right? Now, what you guys are looking at is that model they would have said. Here's the Earth at the center. Now, if you've never seen this before, then that's actually good, right? Because this is not correct, right? This is what people thought. Right? Here's the Earth at the center. Here's the sun going around. Sorry, I don't know why this is blinking like this. Done this, right? Uh, Here's some other planets. Got Mars is right here, right? Right. What you guys looking at? There's a name for this. It's called the Ptolemaic model. Starts with a P after a Greek guy named Ptolemy. Right? He mapped exactly where the planets were night by night, blah blah blah. Right? Something like this. Right? And this almost makes sense until you realize, ooh, guys, look at this loop-de-loo right here. Here's Mars. And what does that mean? From the point of view of Earth, it looks like it's going around, going around, going around. And it makes this retrograde motion. It actually goes backwards in the sky before it goes ahead and continues further. Right? Uh, you can model that. You can put that in your model. Right? And then Mercury and Venus, similar type story. And this particular animation has them orbiting the sun. Did people realize that at the time? Maybe, maybe not. Right? But they also have this like retrograde type motion. Again, you can express this as a model. You can predict like so many years out where in the sky is each of these planets going to be, but there's no like good theory for why it would have this retrograde motion, right? So it's time in the story. Let's bring in Copernicus about 500-ish years ago. Says, well, hang on a minute. What if you put the sun at the center? What would that do to all these motions? It was, oh, that would like greatly simplify the story because now everything is kind of going around this circle type pattern. I think you called it like circular motion, right? Right. Which is a lot closer to the truth, right? There's a little modification we're gonna do, right? But right now, hey, whatever theory you come up with for why some kind of orbit is going on, it probably makes a lot more sense. Or it's a lot cleaner in the math, right? You don't have to worry about a weird retrograde. All that retrograde stuff is just maybe like relative motion like, compared to the Earth, right? Okay, so now we have a huge simplification. Let's do. I don't know, my computer just turned super choppy. I don't know why. I'm sorry. So let's do it. Let's make the best of this here. Okay. I know in the video recording I'm doing, none of the audio is capturing, so I'm just going to narrate this. Do you guys know Carl Sagan, maybe? He's kind of the sort of Neil deGrasse Tyson in 1980-ish, right? Anyway, he had this series called Cosmos. That's where this clip comes from. Here's what Mars looks like from the point of view of Earth, like the Martian orbit path, right? So, oh, look, there's that weird retrograde, right? Again, this is all relative motion, right? The Earth's going around the sun, Mars going around the sun. This is what Mars looks like to us, right? Right. So, right. So after Copernicus, but still before Isaac Newton, is a couple of scientists. One guy named Tycho Brahe, who night after night after night for many years mapped exactly where is the position of Mars in the night sky, right? And then a guy named Kepler got hold of his data and was able to crunch it and figure out exactly how do you describe the orbit of Mars, right? Now, it's really close to a circular path, but it is not exactly a circular path. And by the end of class today, you guys will see why planets don't actually follow naturally circular paths, right? Oh. Now, what was the difference? Here we go, here we go. Here's these two guys, right? So in the background, that's Tycho Brahe. He was watching Mars night after night after night for like years, right? Record the day. And here's Kepler in the front, is eventually about to found Kepler's laws of planetary motion we're going to get into, right? Right. So what's the difference between like what would be a circular path and the actual orbit of, say, the planet Mars, right? Is okay. You guys know what 1 degree is, right? You guys have worked with protractors many times in here. So let's say the horizon is like 0 degrees and the zenith like straight up is like 90 degrees, right? So 0 to 90 degrees in the night sky, right? And you guys don't know on your protractor what 1 degree is. It's a little tiny sliver, like 2 tick marks on the uh, protractor, right? You can split each degree into like 60 minutes, they're called, right? So 1 degree divided into 60 minutes, right? And where Mars would be in the night sky if it was a circular path versus where it was actually observed to be, sometimes was a difference of like 8 minutes. That's like 8/60th of 1 degree in the night sky. That's an extremely precise like difference, right? but that's all it took for Kepler to say, no, it's not exactly a circular path, right? And he eventually realized, oh, actually, it's an ellipse is what it is. That's actually the first law of planetary motion. Planets actually move in ellipses around the sun, right? Not exactly circles, right? And if it's like a comet, it's a highly elliptical path. But planets are pretty close to circles, but not exactly circles, right? Then there's a couple other laws of planetary motion. Okay, so here's a planet going around the star, right? The star, by the way, is at one focal point of the ellipse. You guys remember every ellipse is going to have two focal points, two foci. Okay, so this planet's going around. Do you guys think when this planet is going around this perihelion, like right here, it's going what, a little bit fast or a little bit slow? Little bit fast down here, and at this aphelion, you think it's going what, a little bit slow? Right. So slow down over here, a little fast over here. Should, as a side note, mention that really has nothing or almost nothing to do with the seasons, like summer, winter. That's a misconception sometimes we see, right? The seasons have to do with the tilt of the Earth. So whatever side of the Earth is like tilted towards the sun is getting the summer. So while we're getting the summer in the northern hemisphere, Australia is getting their winter, right? Vice versa, right? So that has nothing to do with this orbital path, right? Okay. So what's the second law of planetary motion? What Kepler also realized is that if the planets will sweep out equal areas in equal times, right? So suppose from wedge point to wedge point, it's like equal times. I'm just to make up some number. Let's say like 20 days, 20 days, 20 days, 20 days, right? Is that right? Well, it's going fast down here and slow up here, but closer and further away. So this wedge has the same area as this wedge here. So that's kind of interesting. Right? It's crazy that he figured this out back when he did, because that's kind of an integral calculus type concept. But this is all before Isaac Newton or calculus was even set down, right? Right. Many years later, Kepler comes across or lays down this third law of planetary motion. Let's look at these laws of planetary motion right here. Oh, I got a poster for it. Right. First law, planets move in ellipses. Second law, equal areas, equal times. Third law, he was looking at the time period for a planet to go around parent star, like 1 year, right? Compared to its average distance from that star, maybe like some radial size of that chart, right? Now this maybe there's like an average radial distance, right? So again, these orbits are kind of close to circles. They're not exactly circles, but they're not crazy far away either, right? And he realized that the square of the time period was proportional to the cube of the average distance within a particular solar system, right? Now that's as far as Kepler got. Now, if you incorporate Newtonian mechanics, and Newton comes after Kepler, you can actually modify this and get a more exact expression, like an equation here. And the equation goes like this: the time for a planet to make one round trip around the star, average distance from that star cubed divided by, and here's the mass of the sun or whatever it's orbiting, right, times what's called the universal gravity constant. I'll show you guys later, right? And then square root all that, and then multiply by 2 pi, you'll get the time to go around. So if you plug in the numbers for Earth, you should get some crazy number of seconds. You can convert to like 365 days. Hey, guys, can I see that? Okay, so Kepler figured out all this just from Tycho Brahe's data. Right. Then let's move forward ahead a little bit in time. Oh, no. Sorry, one more thing on ellipses. I got an activity for you guys. You guys see some string on your desk? You guys see some string? It might be tied into a loop. If it's tied into a loop, you're a step ahead. If it is not tied into a loop, let me show you guys how to tie it, because I always get students who ask how to tie a knot here. Right? So just go ahead and tie a loop if you know what you do. Okay. You don't, here's what we're gonna do. We're gonna cross this over like an X. Right? We're gonna tuck this end around through this loop, kind of like the first step of tying your shoes. You guys see that first step of tying your shoes? Right? And then just repeat that step. Right? So go through, make another loop. Right. Tie that, pull that. Right? And there you go. You have a nice tight loop. Well, you have a nice tight loop right there. You guys got a loop? Okay. All right, now what you do with this, you guys can try this in your notes. Well, you need 3 pencils for this. So if you got 3 times, I'm gonna use 3 pens is what I'm gonna do. All right, those loop right here. It's pen time. Got a couple of dots. And then my third pen. All right, we'll make a triangle. You guys see that triangle? You guys see a nice triangle? You guys make a triangle too in your notes? Right. Then sweep this around. This is kind of like a compass, not a magnetic compass, but maybe like an engineer's compass or architect's compass. Right, sweep around. Right, you guys go all the way around like that. Right. And what shape is that called right there? Ellipse. I'm gonna call it, right? Ellipse. There you go. right? If you were thinking circle, actually it's not too far off. In fact, how could you modify this to make a circle? Yeah, just have one point go around, which would actually be like an actual compass, right? Let me throw that term on the board too, right? Circle versus ellipse, right? So these two points are here. You guys know those are focal points, right? Or the plural is foci, right? There you go. Right. And in terms of planetary orbits, one of those focal points is the sun, and the planet's like going around like that, right? So like that. Right. Let's look at properties of this ellipse. Suppose this is the center of the ellipse right there, that X, right? That's the center of the ellipse, right? And I'll have a couple of arms. I'm gonna have a long arm and a short arm, right? I'll call the short arm A and the long arm B. How about that, right? Oh, and I'm gonna make that a rectangle. Let's do a box out of that. Make a rectangle box. Oh, guys, is the area of that there rectangle, is that just A times B? Is that what that is? A times B, right? All right, question for you guys. And some of my classes got this and some haven't, so I'm about to find out. Somebody here's gonna get this. How many of these rectangle boxes could exactly fill that ellipse? It's close to 3. So earlier, some students said 4. Now 4, you guys see, would be too much because you got this extra wedge here, right? Okay. 3. Pi. Right, I got it. Pi. Yeah. The area of that ellipse is, in fact, pi AB. There you go. Right. And then a circle is a special case of an ellipse, kind of like a square is a special case of a rectangle. Oh, and the area of a circle is, you guys want to say area of a circle? Yeah, pi r squared, right? Right, because it's kind of like the same thing, just apply to like a circle. Right? Next question. What is the perimeter around a circle called a circumference? What is that? 2 pi r. That's right, 2 pi r, right? You guys seen that a couple of times recently. I had you guys do a circle measuring activity. You guys circular motion lab, centripetal force lab. You guys haven't incorporated that as part of your lab, right? So you guys seen this. Right. Last question here. What is the perimeter of an ellipse? How far around is that ellipse? How about this? I can't tell you guys because nobody actually knows. Right? That is a mathematical mystery. So yeah, have fun with that one. Mathematical mystery. Nobody actually knows. Right, now we're ready for Isaac Newton. So Isaac Newton, back during the plague of England, whatever, 1660s, right? Looking outside, sees the apple fall from the tree, makes the connection for the first time in history that, oh, the Earth was pulling down on that apple the same way it must be pulling on the moon. He knows that because the moon is on a curved path, and nothing ever wants to be on a curved path because Newton's first law of motion, law of inertia. So if it is on a curved path, it must be a force. All it must be from the Earth, right? He puts this all together, like two and two together. Right? Okay. And eventually he formulates this, right? That the gravity force between the Earth and the moon. Now the Earth is pulling on the moon. Guys, is the moon also pulling on the Earth? But which force is bigger? Equal. There's Newton's third law right there, right? You got all of Newton's laws going on, right? What is the magnitude of that equal and opposite force, right? Well, it's proportional to each mass. So I'm using capital M for the large mass and lowercase m for the small mass, the Earth and the moon. Some textbooks do M1, M2, right? With subscripts, right? That force is also inversely proportional to the square of the distance between them. Now, the distance between them, guys, is that a surface to surface distance or a center to center distance? You guys see it center to center? You guys see that? All right. So for a lot of the these universal gravitation setups, treat the mass of the planet as being like a single point at its own center of mass, because that's exactly what we're doing here, right? And then it works out okay. Right? Now, why is the force in proportional to the inverse square relationship with the distance? Why is that? Why 1 over r squared? Right? So there's a few relationships you see like that in physics. I'm going to show you guys one with light intensity, right? Because this follows also an inverse square law, the intensity of light with distance, right? Like here, think about this. If you've ever looked at the sun, well, hopefully not. And if you ever do, hopefully not for very long, because you'll go blind, right? So don't look at the sun, you go blind, it'll like burn out your retina. Right? Because it's so intense, so bright. You guys ever look at the stars in the sky? Stars in the sky at night? Yeah. Wait, aren't those just suns too? Just really far away? Okay, so the further away, the less intense. But why 1 over the distance squared? And it has to do with that we live in a 3 spatial dimension universe, right? Yeah. So suppose this candle flame is sending out light in all directions, and we're going to follow 1 cone of light that goes off in 1 direction, right? So it's some distance away, maybe like 1 meter away. There's some amount of light here. Maybe your eyeball's right here, capture all light. It's so bright. So you back up to like twice the distance, like 2 meters away. Right? Now that cone of light, here, guys, look up here, fellas. Now you're 2 meters away. And that same cone of light covers how many times the area that it did before? 4 times, right? Because it was 2 times as tall, also 2 times further back into your page. Oh, yep. Yeah. Right. Guys, so your eyeball, which is like the same area, like your pupil's the same size as it was before, right, is only capturing 1/4 of that original light. Back up to 3 times the original distance. Now that original cone of light is covering 9 times the area. Therefore, your eyeball is capturing only 1/9 of the original light. Guess that? So it's like inverse square relationship. 3 times far away, it's 1/9 of the light. Okay? So gravity turns out the same way. So 1 over the distance squared, gravity, of course, tapers off. Right? We got one more thing to lock this all into place. We got to talk about this G, this capital G, universal gravitational constant. Okay? So let me show you guys what it is, and then some things about this. Right? So universal gravitational constant. There's a number that it's been calculated to be, right, based on observation. Right? It's like 6.67 times 10 to the -11, and then the units go Newton meter squared per kilogram squared. That's consistent with the just rest of it. Just so that, otherwise, it's just proportionalities, right? Force is proportional to each mass, and 1 over the distance squared. It's a big exact equation. You need a constant here, right? And that's what the constant is. Right? Now, nobody knows why it is what it is. It's just been observed to be this number. It's a mystery of the universe as to why any of the universal constants are, but why they are. Why is the speed of light the speed of light? Nobody knows, right? This number right here, guys, is this a very large or very small number? Small. How'd you know it was very small? Yeah, -11 power. Guys, -11 power. Does that make the number negative? No, it just makes it very small. You're dividing by 10, and you're doing that 11 times. That's like 0.02, 3, 4, 5, 6, 7, 8, 6. I take it like that, if I did it right. Newton, meter, square, a paper, kilogram, or something like that. What would that be? Right there? Right. That's a tiny number, right? Oh, we bring in a separate idea here. Did I ever tell you guys how many like fundamental forces there are considered to be in the universe? Right? No? All right. Let's do it right here. Right. They're considered to be 4 fundamental forces. I'll just show you guys right here. Flash over. Right. So one is gravitation. So got gravitationally attracting masses. Right. The other main one we care about in this class is electromagnetism, which covers pretty much everything else. Right? Like if I drop a pin on the surface, is there a normal force from the surface holding it up? But isn't that just electrons against electrons? So that's electromagnetism. How about if I drag it across, friction force? Is that electrons against electrons? That's electromagnetism. How about I pull on a pin, like a tension, or tension in a rope? Is that molecules pulling against molecules? That's electromagnetism. Right? Obviously, electricity and magnetism also that. Right? The other 2 forces are nuclear forces. I'll briefly mention them next semester. Strong nuclear force holds the nucleus together. Weak nuclear force related to radioactive decay. Right? But this semester, really, all we care about is the top 2. Right? Now, within an atom, these 3 guys in the bottom definitely dominate, and gravity is like negligible. Gravity is considered to be the weakest of these 4, right? But at large scale, the nuclear forces don't dominate. Electromagnetism, well, if you think about between the Earth and the Moon, the Earth is basically neutrally charged. Same story for the Moon. So this kind of goes away from the Earth to the Moon. So gravitation takes over at large scales. So different scales, different forces are going to dominate. But, there you go. So we're focused on gravitation today. Gravitation. Okay. Let me flip my screen over and show you guys another Paul Hewitt right here. It's Paul Hewitt time. All right. I'm going to go ahead and mute this and narrate over him because I know the video that I'm recording doesn't record the audio. I think it's a copyright thing. But I'll tell you guys. So he's going to tell you guys an experiment by a guy named Philip von Jolly. Bongelli wanted to figure out what is that universal gravitational constant? How do you figure that out? So he has a scale set up. And on the left side, he has some mass M1, right? And he's got some weights on the other side to balance out the scale. And then underneath M1, he's going to put a big old M2. Now, when he does that, do you think it's going to tip the scale a little bit because there's a tiny, tiny gravitational pull? Right? Now, gravity is a pretty weak force considered to be, but it is going to tip it a little bit, right? So what's going to balance that out is, oh, look, he's putting a weight on the other side of no weight, call it a force, right? Weight's a kind of force, right? Which is going to restore that balance, right? Oh, so now he can calculate. He can figure out if he knows what that mass, what is that distance, separation. Notice he does center to center distance. That's what he just did, right? Right. And he knows Newton's law of gravitation, right? So something about m over r squared is proportional to, right? He can calculate the universal gravity constant, and this the number comes up with 6.67 times 10 to the negative 11. That number has units. It's like Newton meter squared per kilogram squared is what it works out to. It's kind of okay. So that's G, right? And then if you these guys just kind of write in the units there, but that's what I told you guys it was. Right? So kilogram squared there. Oh, he has a fraction within a fraction, but you can take you can kind of reorder that. Okay, so you guys go with that right so far? Okay. Next thing I want to do with this is look at gravity field. Gravity field. Because suppose you are standing at the surface of Earth. Right? You're standing here, surface of Earth, right? Right? And you have some weight. You definitely have some weight. So there's a weight and a normal force on you, right? But what is your weight? Now, I've been calling weight m times g, right? I've been doing that. Right? So you have some mass if you're in some gravity field. You know, that's all fine and good to use like at the surface of a planet. But we're going to get a more universal context because we might be looking at later, like, well, what if you have like a satellite that's way up here where maybe g is like less than 9.8 meters per second squared, something like that, right? So we're going to look at more universal form, or call this f sub g. Did you guys know f sub g is like g m over distance squared, some version of that? That's universal gravity, isn't it? Right? So we got two different perspectives on weight now. Oh, and if this guy is mass m, and say like the Earth now is like capital M, so we got two masses, isn't the gravitational force between you and the Earth, like the Earth pulling on you, right? Some kind of gravitational force, right? That's your weight, right? So what I'm trying to get at is that this lowercase g is this whole gm on r squared. That's what that is, right? That is that. Same thing. And here's your individual mass, like your point mass here, right? Guess that, right? So if you take your weight and divide by your own mass, you get free fall gravity, which is the same for all objects at the surface of Earth. That's the Galileo experiment. You guys remember Leaning Tower of Pisa? Galileo drops stuff off. And then regardless of how massive it is, they all fall at the same rate, right? Right. So let's find free fall gravity for Earth. Right? That'd be universal gravity constant, mass of Earth, divided by some kind of distance squared. Now, what distance are we talking about? We're talking about the distance between you and the Earth. What is the distance between you and Earth from a universal point of view? Is it your center of mass to the center mass of the Earth, which is also the radius of the Earth? Isn't that what that is? Right? Right? So distance between you and the Earth, you might say, well, I'm at the surface of Earth. There's no difference, right? But we're going to treat the entire mass of the Earth as being a point mass at its own center mass, which makes the distance between you and the Earth the radius of the Earth. Okay, right? That's what we're plugging here. Here, maybe I would make this like a capital fixed R, radius of the Earth, gravity field of the Earth, mass of the Earth. Okay, let's plug in some numbers. So gravity field at the surface of the Earth is, so we got universal gravity constant. Bongelli found was 6.67 times 10 to the negative 11 meters squared per kilogram squared. Okay. We got mass of the Earth. I've seen slightly different numbers for this. I'm just going to pick one and run with it. 5.98 times 10 to the 24. And that's kilograms. Right? And then all divided by radial size of the Earth. Again, a slightly different number. The Earth actually isn't a perfect sphere. It's kind of a spheroid. So depending on where you're standing, slightly different numbers. Just pick a number. Let's go 6.38 times 10 to the 6. That's meters. And then don't forget to square that. This might be a good calculator activity. Can you correctly communicate with your calculator? Can you plug that in? So let's try it out. Open parenthesis, 6.67 times 10 power negative 11, close open 5.98 times 10 power 24, close divide by open 6.38 times 10 power 6, close square. All right, you guys got that? Now, you guys know what that's going to come out to. What's the answer going to be? 9.8? Let's find out. 9.799. Yeah, that is 9.8 meters per second squared. Oh, I was going to ask you guys the unit. You guys would have said meters per second squared, though, right? Sometimes you see it this way. I know AP materials, sometimes they switch it up and say, do you guys know an alternate unit for meters per second squared? It's like a Newton per kilogram. That's what it is. Right? So sometimes you see that. Right? All right, there you go. Right. So you guys have either measured that or taken that to be the case so far in this class, and here's like where it comes from, right? Mass of the Earth, radial size of the Earth, universal gravity constant, put it all together, right? Right. Next thing we're gonna do with this is go into space. Oh yeah. Do you guys know the first time in history that people sent anything into space? What year was that? 1950. 1957. Yeah, all right. Right. Now, Newton had this idea back in the 17th century. He said, well, what if you had like a tall mountain that got above the atmosphere? And he took a cannon and he blasted a cannonball. Hey, this kind of reminds me of projectiles. You guys remember cannons on cliffs? Pow. And like land somewhere, right? No, back in projectile time period in this class, we're saying, well, let's blast it so that if the Earth is approximately flat locally, right, then it'll land some distance, right? But now we're considering the fact that the Earth is curved. And if you blast it fast enough, that there's a gravity pull that's pulling on, say, the cannonball in this case, right? So that the cannonball is always falling toward the Earth, but it never actually gets any closer to the surface, right? So it could make like a circular orbit. I wonder how fast would that cannonball have to go to stay in a circular orbit? And oh, that's like a satellite orbital speed of a satellite. Is that right? Yeah. So back in 1957, do you guys know what country first sent up a satellite into space? Yeah, Soviet Union back in the day, right? So freaked us out here in the States because United technology we didn't have. They had nuclear weapons. Oh, what if they start like dropping bombs at us? Well, we better get our act in order, right? Sometimes events happen like that that will shock a country into developing its technology, right? Every time there's a big war, World War I, World War II are classic examples. The government pours lots of money into research and technology accelerates. This was another case. This is what launched our space program, right? We saw the Soviet Union, like, oh boy, we're behind, right? So we launched NASA, right? And so back in late 1950s, you got Soviet scientists, American scientists trying to figure out, oh boy, what is this orbital speed? Because we got to get stuff in space, right? It's a space race. Right? It's on, right? So I bet they pull up their slide rules and they're making calculations that we're about to make right now. We're going to figure out what is that orbital speed. Right. So let's do a free body diagram for that satellite right there. Maybe like Sputnik was the first one, right? Right. What's the free body diagram? What's one force on the satellite? Yeah, wait, gravitational force. So I'll do F sub G, I'm going to call it. We'll look at the universal form of that. F sub G, right? Gravitational force, right? Are there any other forces on that satellite? Nope, that's it. That's the only force. Ooh, does this look like your guys' lab when the top plate of canister was being held by a tension string, right? Hey, that gravitational force is acting as the what force? Keeping it in a circular path. Centripetal. I can say the centripetal force is being provided by the gravitational force, right? Right? Isn't that the setup that's going to start this whole process, right? What expression should I substitute for centripetal force right here? mv squared on r, exactly, mv squared on r, right? Right. We're solving for this v, this linear speed type. Okay. And for gravitational force, should I use this Newtonian universal gravitation right here? Right? Yeah. G m m on r squared. Now let's check out what's what here. So big M could be the mass of the Earth or whatever's being orbited. Take the Earth, right? Little m, that's the mass of the satellite. So big G is universal gravity constant from Von Jolly. Okay? This R could be the distance from the Earth to the satellite. Right? Now, anything in low Earth orbit is about 400 kilometers up from the surface of the Earth, right? And in the big scheme of things, that's actually not proportional to the size of the Earth, not that far from the Earth, right? Here's what I mean. We're just trying to get the satellite above Earth's atmosphere, right? You guys know if Earth was the size of a basketball and you cover that basketball in like plastic wrap, that plastic wrap is about the thickness of Earth's atmosphere, right? So it's not that thick in the big scheme of things, right? And the position of the satellite relative to the center of the Earth is really not that much bigger than the radius of the Earth itself. So I'm going to kind of approximate and say, just simplification, they're about the same, right? So I'm going to use the radius of the Earth right here, right? And the answer is really not that different, okay? Right. So, guys, what cancels out on both sides? Are a little bit, not completely apart, and also the mass of the what? Satellite, mass of the satellite, which even before we get to the answer, that already tells us something. Here, let's see if you guys are following. Suppose this is International Space Station fly around. It's got some astronauts in it, but they got in Hungary, so they need some space supplies. So we're gonna blast them up some space groceries and some new astronaut friends, right? So now it's a lot more massive. Okay, now because it's more massive, does it have to go faster, slower, or the same speed to stay in orbit? Same speed, because the mass doesn't matter, canceled out. In fact, we're one step away from getting the answer. All you have to do, orbital speed, is take square root of both sides. Isn't that true? Just like that? Okay. Oh, let's get a number for this. What's the orbital speed for the planet Earth? Well, it's a big old square root. I need universal gravity constant, 6.67 times 10 to the negative 11 meters squared per kilogram squared. Okay. I need mass of Earth, 5.98 times 10 to the 24 kilograms. I need radial size. I'm just going to use radial size of Earth. Right. 6.38 times 10 to the 6, and that's meters, right? Like that. Okay. This is all band square rooted. Right? And here's a good calculator exercise here too. Right? Can you plug that in? Right? One way you could chunk this into smaller parts. That's okay. But maybe like do the fraction, write that number down, take the square root. I'm going to do it all in one go. Right? All in one go. So I'm going to open up a square root. Okay. Now different calculators work a little bit different. I know everybody has this model because you guys got these on your desk. Right? As soon as I close that parenthesis, it stops square rooting. This model does, right? Or probably any calculator, right? So I know I want everything square rooted. So I'm going to open up an excess of parentheses, and then this particular model calculator will just close anything extra for me. Some calculators force you to close every single one manually, so it depends which model you have, right? But this one will do it automatically. But now I know there's no way I could accidentally close it too early, so I'm going to square root everything, which is what I want. Right? So 6.67 times 10 power negative 11, close, open, 5.98 times 10 power 24, close, divide by, open, 6.38 times 10 power 6. All right, there you go. Right. And make sure after you hit divide by that you also group all those steps together. Right. And then my calculator will close the rest of the parentheses for me. And we're about to find out. Before I hit enter, does anybody actually know how fast is orbital speed? Right, there we go. We're going to find out together. That's what I'm looking for. 7907 to the nearest. And what unit is that? What unit? Meters per second. There you go, because this is speed, meters per second, right? Right? There you go. There's the orbital speed around planet Earth, right? Now, that's for a circular orbit, right? But hang on a minute. I remember Kepler was observing a bunch of planets saying that planets don't actually move in circles. They actually move in ellipses, right? What's that about, right? So here's why you don't actually want a circular orbit, right? So suppose there's a satellite going around at the speed around the Earth, right? Do you guys think that the top of our atmosphere, like there's little air molecules that are escaping into space, right? So our atmosphere doesn't have a definite and it kind of fizzles out, right? So do you think some of those air molecules are like running up against these little Earth orbit satellites and like slowing them down a little bit at a time? What if this number goes down to like 7905 meters per second? What's going to happen to the satellite? It's going to spiral down and crash, right? So a circular orbit is a really fragile situation. So when our solar system was forming 4.5 billion years ago, and like everything was like colliding and all the planets were forming, anything that would have been going in circular orbit, if there was like a little tiny rock that ran into it, boink, then it would have just like spiraled and crashed into the sun. That's why you don't see circular orbits for planets. Right? Now, if you speed this up a little bit, it'll overshoot a circle, and it'll slow down, and then it'll form an ellipse. Okay, so ellipses are more stable. So if it's going like 9,000 meters per second, right? But hey, a minute. What if you keep going faster, 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 like 10,000, 11,000 meters per second? Do you guys think at some point it's going to like fly up into space? And there's a term for that. It's called escape speed, right? Right. I wonder how fast that is. So let's go back to posters here. So we got universal gravitation. We got inverse square relationship. We got there's orbital speed. We just did this, right? Orbital speed, right? Side note on orbital speed while I got this out. You can, if you know the mass of any, suppose you're sending a space probe to Mars, orbit Mars. If you know mass of Mars and how far out you're going to park the satellite, you can calculate how fast it needs to go. Okay. Alternatively, if you send a space probe like an orbit around a planet empirically, and you know how fast it's going and where it is, you can calculate how massive the planet is. Ooh, that's interesting too. So fun stuff you can do with that. Okay, so let's come back. All right, we got now escape speed. You can actually show from conservation of energy, which we haven't talked about yet in this class, but this is how it works out. And if I put these two, so this might come back in the future possibly, right? If I put these two expressions side by side, here's orbital speed, here's escape speed. They're really similar looking, right? Escape speed just has this 2 slipped underneath the square root. If you know what orbital speed is, you just very simply multiply by the square root of 2. You'll get escape speed. Square root of 2 is that like 1.4 something, 1.414, I think, right? So escape speed for Earth, orbital speed for Earth is like about 8,000 meters per second. Escape speed for Earth is a little over 11,000 meters per second. That's how it works. It's like 11.2 kilometers per second. Right? And what this means is if you have, let's put it all together, right? Right. So here's Earth, here's gravity field on Earth for this guy standing on Alaska, right? Here's orbital speed for the satellite, right? If you get a rocket going at this particular speed right here, about 11,200 meters per second for Earth, right? And it's pointing straight away from Earth, and you cut off the engines, and it's just coasting because of inertia. Now gravity's pulling back on it, kind of like if you throw a ball in the air, it's slowing down, it's just going upward. Right? Gravity's pulling down, trying to slow it down. But it still has enough speed at some point so that even though it's slowed down, it can break Earth's gravity and fly away forever, right? Is that now? If the engines are on, if you're on, you don't actually ever have to reach the speed, right? You can just very slowly get away from Earth's gravity. That's okay, right? But if you cut off the engines, as long as you're going at least this fast, then even though it's slowed down, it'll fly away forever. Okay. Right? You guys get there? All right. Let's do let's do this. Question for you guys. There was a polyhut video on this next one too, but I'll just do it in front of you guys right here. Okay. Suppose we got a planet, right? And I got a guy with a shovel. He's gonna tunnel straight down, right? Goes down to like the center, right? Ignoring the fact that it might be molten and all that, but let's say he gets to the center. There's like a cave right in the middle of the planet, right? What would he feel like right in the middle? Would he feel very heavy, very light? What do you think? Huh? Yeah, right. Aha. Right. One of those, right? Right. So, right now at the surface, we know we're all being pulled straight down by the Earth, right? But what if you broke the Earth into like a billion different pieces? So like got all these different grains of sand all over the place. Isn't this guy actually being pulled a little bit that way and that way and that way and that way and that way, like all these grains of sand? But all the sideways components cancel out, and effectively the net result is he's pulling like straight down, right? Straight down, right? But what about if he's like right in the middle? Is he being pulled that way and that way and that way and that way and that way? Right? Hey, what's the net force? 0. Is he floating around like an astronaut? I think he's floating around like an astronaut. Oh, yeah. Right. I think he's floating around like an astronaut, kind of like zero gravity, right? Is that right? Tomorrow, I think I'll take you guys through the full trip of like going down the spiral staircase or going into space. We'll put together a full picture, but just for today, right? I got another story for you guys. Right? Suppose we're flying around in space, right? And exploring the galaxy, and we see some planet. Like, hey, let's go check out that planet. So we land our spacecraft on this planet. Right. Now we're walking around here, got our space shuttle all ready to go. Right? Like, there's something weird about this planet. It feels like it's like lacking gravity or something. I don't know. There's something weird. We're lighter than we should be. We're like bouncing around like on the moon or something. Right? So we're gonna dig a hole, and then we realize real quick. Oh boy. I see what's weird about this planet. This planet's hollow. We got a giant eggshell. We're walking around in an eggshell. Right? Now this planet has some mass. Right? Maybe it's like a couple meters thick or something. Right? So it has some mass. The center mass is still at its geometric center. We can still walk around on it. That's okay. Right? But what happens if you jump inside this hole? Guess what happens on the inside of that planet? Something really weird. Let me show you guys mathematically. Right? And there's an actual application of this. Right? Oh, it looks like just fun trivia of it. Right? Eggshell planet. Right? So we're gonna dig a hole, and well, oops, spoiler alert. Here's what it ends up being. It ends up being gravity-free interior. Let me convince you guys that that's the case. I'm gonna pick a random point on the inside. Random point inside, right? Now, everything above and below is going to symmetrically cancel out. But what about right and left? I want to convince you guys that that also cancels out. Right? Suppose you're at a point where you're 3 times closer to one side than the other side. Right? And so there's some mass of Earth that's pulling, or of this planet, I should say, that's pulling to the right. And there's some mass that's pulling to the left. Let's make like a cone shape and compare these two masses. So there's some mass here. Maybe it's some area of the eggshell times some thickness times some density gives you some mass. Right? And on the left side, if it's 3 times further away, is that 3 times the diameter? That's 3 times as high, but it's also 3 times as deep. Is that 9 times the area? And if it's the same thickness and the same density, that means 9 times the mass. So let's say for force equals gmm over r squared. So gmm over r squared pulling you to the right. What about the left? Well, it's 9 times the mass. So maybe it's 9 times the gravity pull, right? But don't forget, 3 times further away. Oh, but that's being squared because inverse square relationship. Guys, what's 3 squared? Is that 9? Does that cancel with this 9? Ah, so it's the same force pulling you to the left as to the right. So if you step inside this eggshell planet, once you step inside, it's gravity free, right? Now, I'll tell you. Oh yeah. I'll tell you what that's going to be good for. I think tomorrow I'll take you guys through an example of if you're like tunneling into a planet, right? Your weight is going to change as you're going down, like during to the center of the Earth kind of deal. Right? Your weight's changing as you're stepping on a scale. And everything above you in elevation is essentially a bunch of eggshells, like a series of eggshells, like 1,000 eggshells, right? That all individually cancel out because of this right here. So what's left is whatever ground is beneath you in elevation is acting like a little tiny planet. So you actually weigh less and less and less on the way down, right? So probably look at that tomorrow, right? Got a couple other details for you guys today. One is tides. How do they work? So we've been treating the Earth kind of as a point mass all along, but really it's 3-dimensional. And so you got like the Earth and the Moon. You guys know the Moon is the main driver of the tides. There's other effects too. The sun has a little effect, right? But mainly the Moon, right? There's one surface that's closer to the Moon, therefore larger gravity force, right? And then the center of the Earth, there's like a Goldilocks force, right? And then the far side of the Earth from the Moon, well, that has like the smallest gravitational force because it's furthest away. That's why we get 2 tides every day, right? So the Earth is spinning, liquid ocean, 2 tides. Guess that, right? And a similar story with the Moon. So you guys know that only one side of the Moon ever faces the Earth, right? So that's because it's tidally locked, right? No one ever saw the opposite side of the Moon, right, pre-1957, because we never sent anything into space pre-1957, right? We didn't know what the other side of the Moon looked like. Right? There you go. There's tides, right? And one last detail, if I can slip in here, Lagrange points. So these are points of gravitational stability. Between a planet and a star, there are going to be like 5 of these points. So maybe the most obvious one is like L1. L1, sun's pulling to the left, Earth's pulling to the right. There's some point of sort of gravitational stability where it kind of cancels out the gravity fields too, right? But there's some other points too. When you also include this rotational effect, like rotational dynamics. So let's consider L2. A year or 2 ago, there was a space probe sent up to L2, a satellite was, that's actually orbiting L2. Now, why would this be gravitationally stable, right? Well, it is from a rotational frame of reference. So suppose you're looking straight down, you see the Earth beneath your feet. Earth is pulling you to the left. The sun is also pulling you to the left. Looks like you're going to the left. But if you're also along to the right in orbit, you kind of stay in orbit, so you don't actually fall any closer to the Earth. This is kind of gravitationally stable. L3, similar type story. Pre-1957, there was a lot of speculation there might actually be sort of a mirror Earth over here that we could just never see, right? People thought there might be. Nowadays, we know there isn't because we can look back there and we won't see anything there, right? But there was thought there might be. Right? There's a guy named Lagrange who did some crazy math and realized that L4 and L5 also exist. These are actually the most stable gravitational spaces. I do have a GIF to back that up. Let me see. We're gonna show you guys this right before the bell rings on us here. Let me prove that to you guys. There's something called the is this gonna not pull up? Well, come on. There you go. Okay. But here, I'll have to pause this. We'll have to continue the story tomorrow because that's about the end of class right there. Right there, Z's.